Hello there. My name is Chris Fernandez. I'm a solutions engineer for Keysight Technologies. I am based on the Northeast side. And today here, I'm just going over clip number one of three. I'm gonna actually go through the first movie. Our first clip is gonna be about MACSec fundamentals in terms of how we tested in using IX network. And the second video is going to be about layer 2, layer 3 MACSec and how to configure it and how to test and what things are we looking at. And the last video is going to be about layer 4 using the app library to do decryption on the fly as we test MACSec. So as we get started here, we can talk about a little bit about MACSec, what it is. It's a secure point-to-point Ethernet link. It encrypts the layer 2 and everything that goes beyond that. It offers data integrity, data confidentiality. Since the data is encrypted, the integrity comes as part of a field that gets embedded in the packet to make sure that you are getting whatever you send out. And replay protection, that's done by um, adding a packet number. So we know that if attack in the min and the middle attack happens, you know that the packet number should be. So the advantages is that it's a hardware-based line rate encryption for high-speed Ethernet. So it's at the lower level, and you can go up. You can encrypt everything from layer 2 and up, um, just using MACsec encryption. So all the protocols, the layer 2 protocols, are also encrypted, has a strong encryption protection and lower overhead. Provides you can actually do authentication using 802.1x. As of right now, as I'm speaking and talking, um, we don't have 802.1x on the MACsec stack yet. It's on the roadmap and should be available in the near future. This is just a little bit about the terminology that we talk about. CA, CS, secure channel, the secure channel identifier, the secure association and what it does, and the relationship between AN, association number, is the number that's concatenated with your MACsec secure channel identifier to identify a secured association. In the case where you have end station, for example, you don't need the secure association because there's only one item or one entity on that link. And then the connectivity association key, the connectivity association key name, which is points to the CAK, the secured association key that is used to encrypt and decrypt traffic given by a session. And then the key encrypting key is used to protect the MACsec when the key server distributes the keys to the CA members. Um, the ICK is part of um, it's a it's a field that gets embedded in the packet when it gets encrypted. And master key, it's the master association key, and KS is the key server, which is responsible for selecting, advertising cipher suite, generating and distributing the SEC, which is the key for all. So a little bit of the overview in the tag here. As you can see here, you have after destination and source MAC address, the MACsec header comes in. In the MACsec header can be either 8 bytes or 16, depending on if you have included CSI or not. The 8 bytes association here. And then you can have your VLANs in the payload, which can be encrypted or decrypted. And then the ICV here, which I talked about earlier, is what makes the integrity part of the packet. So you can make sure that the packet that you send out is the correct packet that you received. And the CRC, which is part of the Ethernet header at the very end. And the MACsec ether type is always set to 88E5. That's how the upper layers know that this is a MACsec packet. And as I said again, the integrity check value ICV is 16 bytes here. It's at the very end of the packet. So this is the breakdown of the TCI field in the MACsec. So this is part of this bit here inside of the MACsec header here. this TCNI here. This is I put it down here. It's just to illustrate of what are those bits are used for, or those 8 bits are used for, because in IX network you can actually change them to create negative scenarios to see how the DUT will behave when the bit that is set to, for example, a single copy to broadcast or something like that. So you'll be able to manipulate those single bits individually inside of the IX network. The MACSec, it's based on two IEEE standards, AE 2018 for Mac media access control, MACSec security, and 801.2x 2020, which is port-based network access control. Again, the 802.1x is not part of the Keysight's offering right now. And then you can see here the two cipher suites that we support is 128 and 256, and the extended one, the extended packet number with XPN. This is in case that you're doing rekeying and the packet number um, can increment at a lower rate when you're at high speed. So, and we support VLANs, either clear text or encrypted. So that's part of our offering as well. And confidentiality offset can be 0, 30, and 50. So the 0 is the default, but you can set it to either 30 or 50. So you kind of move your encryption to the inside of the packet in case you need for a specific header here. Some implementation challenges here. So I just wanna highlight a couple things about MACSec. One is the buffer overload. So the way you think about it is when you have a device that is not part of the MACSec, and he's blasting packets over to a switch that's going to do the encryption. What happens is that the switch now can be receiving a packet that he's plus going to be adding up to 32 bytes of uh, things inside the packet, right? So he has to actually uh, add stuff to the packet. That means that the packet is going to get bigger. So one way what can happen is that the device is sending packets so fast to your switch, for example, that it can't keep up because the packets have to be encrypted and send it out. Not just the size, but the encryption part of the transmission. So one thing that we can talk about is there is some way to deal with this problem is actually adding some bytes to the inner gap frame before the packet gets encrypted. So the calculation here on the right side here, it talks about uh, initial packet size of 64 bytes and the encryption being 96 bytes on the overhead, MACSec overhead. Um, and then you're talking about the standard frame gap is about 20 bytes. That means that if you want to keep the same 20 bytes at the end after the packet is encrypted, you need to add about 12 bytes of inner frame gap on the sending part, on the source part. So the encryption and decryption part will kind of make the packet bigger and smaller, but you won't have buffer overload because now you're getting packets at the same timing that they're being sent out. We were talking about MTU considerations as well, since the packets can be added to another 32 bytes. So you have to make sure that the packet that's being received is less than 1486 to make sure that you don't overload the MTU. Latency, this is about how long it takes for your device, even though it's a hardware-based CPU doing the encryption, that encryption and decryption can add some latency to the packets. And another thing that you have to be aware of is if you have a switch that is connecting a, a bunch of devices or ECUs in a car, for example, and that specific switch fails, then you have a multi-failure of the whole system, right? You have many ECUs kind of now offline because that single switch failed. So could be a single point of failure in terms of MACSec. There's three steps to the MACSec component, right? One is the 82.1x where you do the authentication to bring it in, and that's when you start doing the MKA. The MKA is where you kind of decide who's going to be the key server at that point. And then the encryption decryption part itself, that's like a third step of the process here. The first two steps, the 802.1x and the MKA, which is the protocol used for the key server, uh, choosing the key server, those can be done in software. That's easy to do in software. It doesn't require too much power, but the encryption decryption usually gets done by the hardware if performance is. In Keysight, we have two solutions for MACSec. We have a software-based MACSec and a hardware-based MACSec. Um, you can see here on the screen the difference between them and what do they actually what's the difference between them and the hardware-based MACSec. It's actually right now only available in one hardware that is dedicated for that. It's only two ports, but there's a lot of power hardware associated with that to do the encryption decryption at line rate. And you can see here the difference between the two. So rekeying, for example, is not available when you're doing um, static SACs on the software based, and it's always available on the hardware base. There's a few other differences here and how we do frame rates, availability on the software based and non, and the tracking for the packets as well. In the software-based solution, what we do, we encrypt the packet and we send it out to the FPGA to be transmitted, and that the latency or that um, in that solution, kind of the penalty for that is that we lose the ability to do um, stats to put some markers in the packets for us to figure out the tracking for the packets. And that can be easily done on the hardware. Plus, on other protocols can only be done on the hardware level. So there's a few differences here. But for you to test MACSec, in most cases, the software base is enough. Order information. This is the part number. On the left side here, you can see that the hardware-based MACSec is only available on ARIS-1 400 gig high performance QSF PDD, and the software-based MACSec is available in our ARIS-1M 800 400 gig, as well as the Novus line load modules, and the Novus 1 Plus, which is the one that has a Novus card in there. And on the right side here is the part numbers for the specific um, MACSec functionality to be turned on, either on the chassis or ARIS-1 on the Novus Plus 1. And there's actually a bundle here for if you're looking into the ARIS-1T, the bundle, the software bundle. And that's pretty much it for this presentation. I'm going to go over now on the second video and talk about the software-based MACSec using static MACSec on IX network, showing you how to configure it and how things look.